Challenges of data. Now, containers have changed the way we build, ship, and run applications. This transformative technology affords great velocity and application portability, but has also brought new challenges to technology teams. The challenge of persisting data in a transient system. As I've already mentioned in the introduction, Kubernetes is the leading orchestrator for container workloads. So let's discuss a particular scenario. What if a container stops for one reason or another? Kubernetes is definitely able to start a new instance almost immediately, making availability and recoverability something that happens in seconds as opposed to minutes or even hours. But this new instance of the application may not have access to the file system from the old instance, especially in the case of local file systems, so additional orchestration is required to ensure that the stateful component of the application is bound to the instance at restart. This focus on stateless applications and epithermal systems have prevented certain stateful and complex applications from being a good fit for this revolutionary technology. As companies look to bring applications into Kubernetes, the inability to persist data through a container's lifecycle is undesirable. People need a way of dealing with stateful applications and persisting data, all without inhibiting the positive aspects of the self-healing capabilities of the Kubernetes platform. Now, to get a better sense of how to address challenges in Kubernetes, we'll take a look at one of the earliest challenges that have been successfully addressed, that is handling log data. The Kubernetes community found a successful way to address log data by sending it to an external system. Now, by using solutions such as the Elasticsearch, Logstash, and Kibana stack, you have a pattern of leveraging an agent in a container alongside different applications. Now, the process enables developers to send logs to a standardized endpoint, which makes it portable and flexible. In the enterprise, moving storage into external system isn't something new or unique. The use of a storage area network, that is SAN, has been a staple practice of enterprises for a large number of years. But typically, it has been implemented by delivering a pre-configured, dedicated volume to a virtual or physical machine. So now the next question that arises is, how do you provide a stable storage solution for any type of content with an equally composable and portable convention as the EKL pattern? Firstly, you do not want to inhibit your IT team's abilities to back up, recover, or secure the data either. Fortunately, this is where Kubernetes enters the picture. Its features and capabilities address this challenge as they are rapidly growing and maturing. Kubernetes began with the storage features as part of the pod API and soon expanded these into standalone interfaces, which include volumes, persistent volumes, storage classes, and container storage interface. In the previous sentence, if you noticed, I mentioned the word pod. You must be wondering what pod is, right? A pod is simply the smallest schedulable resource in Kubernetes. It is a logical collection of containers which ensures the encapsulated containers share resources and are hosted on the same node in your cluster. So typically a pod really contains of a single container and is an instance of an application. Now let's move on to the next topic of this session and discuss volumes in Kubernetes. The Kubernetes volume in its simplest form is a directory that's attached to a pod and mounted to one or more containers in the pod. Such coupling is tight and is a foundational construct for how data can be presented to a container. Now, because of this relationship with the pod, Kubernetes volumes are designed to have the same life cycle as the pod. If an epithermal volume is defined by the pod, for example, its contents do not survive a container restart. Now, when a pod is removed from Kubernetes, any volume relationships are broken and epithermal volumes will be destroyed. Kubernetes volumes are typed, which is how you define the storage mechanism backing the volume. Volume characteristics may be defined via volume type specific parameters. This may be a physical disk or path on the Kubernetes node, ASAN, a network attached storage, or even a storage service from a cloud provider, to name a few. So what really volumes do is it really allows applications to have a very defined storage part that stays consistent through the redeployment of a container. Okay, So this layer of abstraction really helps, but on its own does not solve all persistent storage concerns. There are many special volumes available for use like the empty directory, config map, secret. So all of these have their own advantages and can be used in many ways. When a pod is scheduled to run on a node, a volume is created on that node and will remain there until the pod is deleted or moved to another node. This volume is an empty directory volume that begins empty and is backed by the storage of the host itself. The other two types of config map and secret are volumes whose content is actually stored by Kubernetes. This mechanism is often used to pass configuration information, such as credentials, into a container and ensure they are available wherever the pod is scheduled to run. Now that we understand volumes just allow applications to have a defined storage path that stays completely consistent and same throughout the redeployment of a container, let's move ahead and talk about persistent volumes in Kubernetes. Now, as the relevance and utility of local storage options are literally exhausted, the need arises to leverage external storage. Individual nodes may have storage provided by a SAN, but that's not the same as being able to orchestrate the external storage along with the rest of the instructions for managing an application. Kubernetes here provides a persistent volume claim, which is a request for storage. So the request made by the persistent volume claim defines characteristics of the storage that are desired by your application, such as access and volume modes, size of volume, selectors, storage cache, all of that. In conjunction with PVCs, that is persistent volume claim, Kubernetes also provides a persistent volume resource. Okay. So a persistent volume has historically been a pre-provisioned storage volume, but more commonly is provisioned from a storage class dynamically and made available to the cluster for use by a pod. So persistent volume is simply a piece of storage in the cluster that has been provisioned by an administrator. And it also provides a persistent volume claim, which is basically a request for the storage. And you can see all of this represented in the diagram on the screen. In a Kubernetes cluster, when you create a storage class, you define provisioners, parameters, and reclaim policy. Provisioners are the utility or component responsible for interacting within the backend storage system, whereas parameters helps in the setting or values that you can pass to the provisioner. The reclaim policy instructs Kubernetes to either retain or delete the volume when it's released. If your volume is retained, you may need to perform your own volume cleanup and maintenance. To make storage systems support more extensible, plugin-based storage driver mechanisms are really important and necessary. So instead of only developing and shipping storage drivers as part of Kubernetes itself, storage vendors and users wanted a way to provide and use the drivers they need and to omit the ones they do not. So along came CSI and Flex Volume, which are the out-of-tree extension points for storage drivers. Both of these plugin types allow for administrators to deploy storage drivers that can be loaded dynamically by Kubernetes nodes, and both provide the ability to provision volumes of any number of storage types. Flex Volume was introduced first, but CSI is emerging as a more dynamic and comprehensive specification. Flex Volume is included for completeness, however, the convention is being only deprecated. Only use it if you must. On the other hand, the CSI specification outlines a number of storage operations in a way that can extend to additional container orchestration platforms. Now that we understood what are volumes and persistent volumes in Kubernetes, let's move ahead and talk about why do containers need storage. Okay, so when you think of adopting a new application architecture, such as, cloud native, it seems really logical to do with a new application. More times than not, however, you do not find yourself only developing new applications. If you're like most folks, you have to blend the traditional needs of applications and the functions they serve while applying emerging application architectures to improve speed, adaptability, and costs. Now, at this point, Kubernetes and the real world collide, and storage is a big part of this transformation. So I'm sure most of you are aware that you build business applications in containers. They implement business logic, automate decisions, and really set out to make our lives much easier. Your applications also produce a lot of data. It may be in the form of files, data tables, reports, and much more. Building small functional bits of logic into containers is a very good decision, but what would you do with so much data? Now, without storing data in a persistent volume, the file system of a container is also epithermal. Now, when a container restarts, the file system is reset to whatever the file system state is in the container's image, and files not stored in a persistent volume do not survive the restart. You really need a sustainable and supportable way to store data and objects in flight or as output from your applications while taking advantage of the portability, scalability, and recoverability of containers. Now, instead of fighting the natural tendency of containers to be stateless and lightweight, the pattern looks to augment Kubernetes to facilitate the behaviors we want. If your Kubernetes cluster has access to or is in public cloud providers such as AWS, you have the platform services that can provide block devices, file system as a service like Elastic File System, databases as a service like Relational Database Service, and object storage like Simple Storage Service. Now, each of these offerings have individual performance characteristics, that is, they have their own pros and cons, and you must align your application and workload with the proper type of storage for its needs. This alignment requires multiple unique methods and processes for orchestrating the various storage mechanisms, and not all are aligned with the way the application is orchestrated by Kubernetes. GCP, AWS, and Azure all have storage drivers in Kubernetes that help offload the concerns of managing and provisioning the platform storage services and provide a common interface in PVCs and storage classes. But how do you achieve parity for clusters running inside corporate data centers or for storage services you wish to use when a consistent experience in Kubernetes doesn't exist yet? There's one solution, which is to host your own storage system. So let's move ahead to the next part of the session and check out the storage solutions in Kubernetes. Hyper-converged infrastructure is the combination of compute, networking, and storage, all implemented as software and all deployed on the same nodes. Now, this software-defined approach introduces immense flexibility in the underlying hardware, eliminating dependency on specific vendors and specialized components. It also affords IT teams the ability to achieve portability and consistency of management and configuration. Rook is a storage orchestration for Kubernetes. It uses the declarative nature of Kubernetes to make storage services self-healing, self-scaling, and managed with similar conventions as your containerized applications. Rook uses a plugin extensible architecture to help you automate storage administrative tasks such as deployment, bootstrapping, configuring, scaling, provisioning, and monitoring. So, what does this really mean? Rook allows you to use a declarative style of management that really empowers you to achieve as code capabilities for a multitude and various types of storage types. It implements the new necessary Kubernetes objects so you have a common interface to provision storage software that provides object, block, and file system storage types. That is, Rook goes way beyond primitive storage types and also really enables you to orchestrate databases and other storage types in a claims-based fashion. This common way of dealing with volumes and now other storage types in Kubernetes is one way it is growing to orchestrate all of the storage types. So Rook on its own isn't a storage system. It must be coupled or collaborated with a portable storage subsystem or service. So Rook has operators to support the following storage backends, and one of it is Ceph. Ceph is a high-performance distributed storage platform designed to bring similar capabilities found in GCP and AWS to any cloud platform such as Kubernetes. It provides object storage, block storage, and distributed file systems backed by a single reliable storage cluster, which is running on commodity server hardware. Ceph is designed to be extremely scalable. It is based on the reliable autonomic distributed object store that is a self-healing system that distributes and replicates data safely across storage nodes. It then layers a distributed file system, block storage service, and S3 compatible object storage service on top of RADOS, that is the reliable autonomic distributed object store. So there's a huge advantage of using Ceph, that is, it is open source and purely software. It can really provide its rich set of storage capabilities and features when deployed across almost any server hardware and either hard drives, SSDs, or any combination of the two. It is widely used in a range of environments, especially private cloud deployments, but it can be complicated to properly provision and connect a Ceph system to Kubernetes. Rook simplifies the deployment and management of Ceph itself and also provides an extremely simple and Kubernetes native way to provision storage services. So some of the storage best practices are with the persistent volume settings, limiting the storage resource consumption, and definitely making requests and limits on the resources. So the persistent volume life cycle is independent of any particular container in the cluster. Persistent volume claims are a request made by a container user or application for a specific type of storage. So when you're creating a persistent volume, you will have to follow its rules. Okay. The next best practice is to limit the storage resource consumption. It is definitely advisable to place limits on the container usage of storage to really reflect the amount of storage actually available in the local data center or even the budget available for cloud storage resources. There are two main ways to limit storage, that is resource quotas and storage classes. The next best practice is to implement resource requests and limits. Kubernetes provides resource requests and resource limits that really help you to manage resource consumption allowed for individual containers in Kubernetes. So a resource limit can be specified for some temporary storage. Okay. So setting storage requests and limits can help prevent containers from being constrained by resource scarcity on container hosts or taking up too many resources unexpectedly. With this, let's move on to the case study. So the case study that we'll be talking about today is by using a cloud provider storage service to externalize data from the container. As you can see in the figure, you can see the implementation of the application and storage patterns in a progressive fashion. You can use each of these application and storage patterns in the HCI system. Okay. You can also see an application that consumes storage via a persistent volume. And if you move from AWS to a different provider such as Google, you can provision the application in the exact same way. However, if you're running Kubernetes on premises, there is no pre-existing storage service to consume. So here in the figure, an application is attached to a persistent volume backed by Amazon EBS. So now what the application can do is they can use a storage provided by Rook, Ceph, or another software-defined storage solution, which is in turn consuming compute and storage resources from any cloud provider. Okay, so it shows your application deployed to a hyper-converged cluster, and the diagram really illustrates your ability to make your applications portable across similar HCI clusters hosted in two different providers. It is really critical to point out that this is accomplished with only one set of orchestrations to manage applications and storage, thanks to the common interfaces and consistency provided by Kubernetes plus the Rook and Ceph combination. You can now move your applications as is between providers now. So the diagram that you see has an application that consumes persistent volumes that are provided by Rook Ceph in any environment. Firstly, we will understand why do we need ingress. So when you're creating pods in Kubernetes, you assign selector labels to them. You can see these labels in this snippet of a deployment manifest on the screen. So this deployment.yml file, what it does is it creates three replicas that run the Docker image, my app, and assigns the app that is equal to the FOO label to them. Rather than assigning the pods directly, it is typical to group them under a service, which makes them available at a single cluster IP address, although only from within the same cluster. The service also acts as a layer of abstraction that hides the ephemeral nature of the pods, which can be scaled up and down or replaced at any time. It performs rudimentary round-robin load balancing. So, for example, on the screen, you can see the following service definition, which collects all the pods that have a selector label app is equal to FOO and routes traffic evenly among them. However, the service is accessible from inside the cluster only, by other pods that are usually running nearby. So Kubernetes operator grappled with how to give clients outside the cluster access. The problem was pretty apparent early on, and two mechanisms were integrated directly into the service specification to deal with it. So when you're writing this service manifest, you can include a field that is named type, which takes a value of either node port or load balancer. So the example snippet that you can see on the screen sets the type to node port. So let's firstly talk about services with a node port. So this type are typically very easy. They essentially announce that they'd like the Kubernetes API to assign to them a random TCP port and expose it outside of the cluster. What makes this more convenient is that a client can target any node in the cluster using that particular port, and their messages will be relayed to the right place. For example, it's like saying you can call any phone in India and whoever picks up will make sure you get forwarded to the right person. The only downside is that the port's value must fall between the range 30,000 and 32,767, a range safely out of the way of well-known ports, but also conspicuously non-standard compared to the familiar ports 80 for HTTP and 443 for HTTPS. The randomness itself is also a hurdle, since it means that you do not know what the value will be beforehand, which makes configuring NAT, firewall rules, etc. just a bit more challenging, especially when a different random port is set for every service. So the other type of option that is available to set type is to load balancer. However, this comes with some prerequisites. It only works if you're operating in a cloud hosted environment like Google's GKE or Amazon's EKS, and if you're okay with using that cloud vendor's load balancer technology, since it is chosen and configured automatically. The most costly disadvantage is that a hosted load balancer is spun up for every service with this type, along with a new public IP address, which has additional costs. So allocating a random port or external load balancer is easy to set in motion, but comes with various unique challenges. Defining many node port services creates a tangle of random ports. Defining many load balancer services leads to paying for more cloud resources than desired. It is definitely not possible to avoid completely, but perhaps it could be reduced, contained, so that you would only need to allocate one random port or one load balancer to expose many internal services. The platform needed a new layer of abstraction, one that could consolidate many services behind a single entry point. It was then that Kubernetes API introduced a new type of manifest called an ingress, which offered a fresh take on the routing problem. So it works like this. You write an ingress manifest that declares how you would like clients to be routed to a service. So the manifest here doesn't actually do anything on its own. You must deploy an ingress controller into your cluster to watch for these declarations and act upon them. Ingress controllers are just pods, just like any other application, so they're a part of the cluster and can see other pods. They're built using reverse proxies that have been active in the market for many, many years now. So you have your choice of an HA proxy ingress controller, an NJX ingress controller, and much more. The underlying proxy gives it layer 7 routing and load balancing capabilities. Different proxies bring their own set of features to the table. For example, the HA proxy ingress controller doesn't really need to reload itself as often as the NJX ingress controller because it allocates slots for servers and fills them in it at runtime using its runtime API. That can eventually lead to better performance. Being inside the cluster themselves, ingress controllers are susceptible to the same world in jail as other Kubernetes pods. You need to expose them to the outside via a service with a type of either node port or a load balancer. However, now you have a single entry point that all traffic goes through, one service connected to one ingress controller, which in turn is connected to many internal pods. The controller, having the ability to inspect HTTP requests, directs a client to the correct pod based on characteristics it finds, such as the URL path or the domain name. So in short, ingress is an API object that manages external access to the services in a cluster that is typically HTTP. Ingress may provide load balancing, SSL termination, and name-based virtual hosting. There are definitely some terms that you'll have to be familiarized with, such as node, which is basically a worker machine in Kubernetes, which is a part of the cluster. Also the meaning of cluster, which is a set of nodes that run containerized applications that are managed by Kubernetes. An edge router, which is a router that enforces the firewall policy for your cluster. This could be a gateway managed by a cloud provider or a physical piece of hardware. And I'm sure you know what a service means. A service is simply a Kubernetes service that identifies a set of pods using label selectors that we've already discussed in the previous part of the session. Cluster network is simply a set of links, logical or physical, that facilitate communication within a cluster according to the Kubernetes networking model. So what Ingress really does is it exposes HTTP and HTTPS routes from outside the cluster to services within the cluster. Traffic routing is controlled by rules defined on the Ingress resource. So let's take a simple example wherein Ingress sends all of its traffics to one service. An ingress may be configured to give services externally reachable URLs, load balance traffic, terminate SSL or TLS, and offer name-based virtual hosting. An ingress controller is responsible for fulfilling the ingress, usually with a load balancer, though it may also configure your edge router or additional front ends to help handle the traffic. An ingress does not expose arbitrary ports or protocols. Exposing services other than HTTP and HTTPS to the internet typically uses a service of type service.type is equal to node port or service.type is equal to load balancer. So firstly, you must have an ingress controller to satisfy an ingress. Only creating an ingress resource has no effect whatsoever. You need to deploy an ingress controller such as ingress NGX, or you can choose from a number of ingress controllers. Ideally, all ingress controllers should fit the reference specification. In reality, the various ingress controllers operate slightly different. So firstly, we will look at how a minimal ingress resource looks like. So as with all the other Kubernetes resources, an ingress, as you can see, needs API version, kind, and metadata fields. The name of an ingress object must be a valid DNS subdomain name. Also, ingress frequently uses annotations to configure some options depending on the ingress controller, an example of which is the rewrite target annotation. Different ingress controllers support different annotations. The ingress spec that you can see, that is the specifications, has all the information needed to configure a load balancer or proxy server. Most importantly, it contains a list of rules matched against all the incoming requests. Ingress resource only supports rules for directing HTTP or HTTPS traffic. So let's move ahead and talk about ingress rules. Firstly, you'll need an optional host. Now in this example, no host is specified. So the rule applies to all inbound HTTP traffic through the IP address specified. If a host is provided, for example, foo.bar.com, the rules apply to that particular host. Secondly, a list of paths, for example, front/test path is required, each of which has an associated backend defined with a service.name and a service.port.name or service.port.number. Both the host and path must match the content of an incoming request before the load balancer directs traffic to the reference service. And finally, you'll need a backend, which is a combination of service and port names. HTTP and HTTP requests to the ingress that matches the host and path of the rule are sent to the listed backend. A default backend is often configured in an ingress controller to service any requests that do not match a path in the specification. With this, let's move ahead and set up ingress on the default Kubernetes cluster, that is Minikube. So now what we're going to do is we are going to set up ingress on Minikube. So before we move on, there are some prerequisites. Firstly, you will have to have Docker installed. You have to have an hypervisor installed. You will also have to have Minikube. You'll also have to have kubectl, that is the command line interface for Kubernetes, installed along with Minikube. Okay, so if you want to install all of these tools, firstly, you will have to install Docker. And for this, you can just go to the official website of Docker and you can check out the version that you want to install. Now, currently, I'm working in the Linux virtual machine, so I'll want to install Docker for that. So I'm going to go to the official website of Docker. I'm going to click on Get Started button, which is present on the right-hand side. And if I just scroll down, you can see several options. You can play with Docker. You can sign up for Docker Hub, which is basically a website or a cloud-based application registry for collaboration purposes. So now what I'm going to do is I'm just going to scroll down and I'm just going to click on Docker Desktop. There are various options you can download for Windows, you can view for Linux engine, you can download for map, and I'm just going to click on for Linux. And this will redirect me to a page where I can just install the Docker engine, right? I have to install the Docker engine for the Ubuntu community, and I can just do that. So I'm just going to click on this. So this will redirect me to a page where I can install Docker. So if I scroll down and click on this link, I can install Docker engine on Ubuntu. Okay, if you want to uninstall the older versions, you can simply execute this command. If I scroll down, you can see that there are various ways you can install Docker into your Linux machine. The most convenient way to install Docker would be by using the repository. So there are some steps that you can follow, and you can update the app package index and then install packages to allow the apt to use a repository over HTTPS. Then you can add the Docker's official GPG key using this command. And then finally, you can execute this command based on your architecture, your system's architecture. And then finally, you can move on and install the Docker engine. If you want to install a specific version, you can just mention that too. You can select any of the versions that you'd like to install and then execute the command accordingly. Okay, once that is done, you can just verify that Docker engine is installed correctly by running the hello world image. And I'm just going to copy that. And since I've already installed Docker in my virtual machine, I'm just going to execute this command and check if Docker is up and running. You can see a message that says hello from Docker, and you can see that this message shows that your installation appears to be working correctly. That's great. So we have Docker installed in our virtual machine. Okay, now what I'm going to do is I'm going to open a new tab and I am going to install Minikube. Okay, so I'm just going to look for Minikube and kubectl. If I scroll down, you can see that there is a web page that says install tools, and I'm just going to click on that. So it redirects me to a page where you can choose the tools, the Kubernetes tools that you can install in your local machine. There's kubectl and there is kind and there's Minikube. We don't really need to work on kind and kubeadm. So we're just going to be working on kubectl and Minikube. So that's what you will have to install first. So before you install Minikube, there are some prerequisites. Firstly, you'll need 2 CPUs or more. You'll need 2 GB of free memory. You need 20 GB of free disk space, internet connection. You'll need container or virtual machine manager such as Docker. That's the best thing. And also you will need Hyper-V or KVM or HyperKit, any of that, okay? And you'll also need a Hyper-V or KVM or VirtualBox or VMware, any of that installed successfully in your local machine. And once that is done, you can go ahead and install Minikube or you can install kubectl. So since I'm installing kubectl, which is simply a command line tool that will allow you to run commands against Kubernetes clusters, you can just click on the install Kubernetes option on Linux. And again, there are some prerequisites that you'll have to follow. And you can just scroll and you can see that there are 3 ways to install this into your local machine. The first one is you can install it by using the kubectl binary with curl on Linux. You can install using native package management, and you can also install using other package management. I would suggest or recommend you to install kubectl binary with curl on Linux. So there are a few steps. Firstly, you will have to download the latest version with the command. Then you have to validate the binary. And then finally, once the validation has been successfully done, you can install kubectl. Okay. And since I've already installed it in my VM, I'm just going to check the client version of kubectl. So you can see all the information of the client version, the Git version, the Go version, the platform that it is currently on, working on, the build date, all of that information is given here. That's great. So once you've successfully installed kubectl, we will go check out how to install Minikube. Okay, so first here you'll have to select your operating system. Okay, you have Linux, you have Mac OS, you have Windows, the architecture type, and there are three options. That is the binary download, the Debian package, and the RPM package. Again, I would suggest you to pick your choices according to what you're comfortable with, and then finally install Minikube on Linux. So as we all know, this is a cluster. Minikube is basically a cluster, right? So you can start your cluster by simply executing the Minikube start command, and then you can get on with the interaction. Okay, so what we're going to do is, since I've already again installed, I'm just going to execute the start command. Before that, I'll just clear my screen. So once I have cleared my screen, I'm just going to execute the Minikube start command. So as you can see that Minikube is up and running. It says kubectl is now configured to use Minikube cluster and default namespace by default. So that's great. We have a namespace that is created and that is named as default. We also have the Minikube cluster up and running. So I'm just going to clear my screen. And now what we're going to do is we are going to enable the NGX ingress controller. As I've already mentioned in the previous part of this session, we will have to enable the ingress controller. Then only we can move ahead and create our resource, right? So that's what I'm going to do. I'm just going to enable my NGX ingress controller by using the command minikube add-ons enable ingress. So for this command to execute, it's going to take you a minute or two. So I recommend you to be a little patient. And once that is done, you can see that the ingress add-on has been successfully enabled. Okay. Once that is done, what we're going to do is we're going to verify that the NGX ingress controller is up and running. For this, I'm just going to execute the command kubectl get pods -n kubesystem. So I've just opened the link and you can see that the output is Hello World version 1.0.0 and also the host name has been specified. You can now access the sample application via the Minikube IP address and node port. Okay. So what we're going to do is we're going to access the application using the ingress resource. Okay. So firstly, we will have to create an ingress resource, right? I'm just going to clear my screen. So there is a file which is an ingress resource that sends traffic to your service via helloworld.info. So first we are going to check out the file. So for that, I'm just going to go to my web browser. So I just have the link of the YML file and you can see that the YML file has the API version, the kind, the metadata, the specification, the rules. We discussed the rules, right? So all of that has been specified in this YML file. Now what we're going to do is we're going to create this YML file, right? So I'm going to switch back to my terminal and I'm just going to use the kubectl apply command. So I'm just going to type out the file that it has to fetch. I'm just going to cross check if it is right. And once that is done, I'm just going to execute it. So you can see that the example ingress has been created. Okay, so we're just going to verify the IP address is set. And for that, we're just going to use the command kubectl get ingress. So you can see that the example ingress has been created successfully and it hosts helloworld.info and there is an address, its ports, its age, all of that information has been given. Okay. So now what we're going to do is we're going to add the IP address to the bottom of the etc host file. So for that, what we're going to do is we are simply going to edit the file. I'm just going to execute the command vim host. Okay. So now that it is open, we can edit it. So once I get on the insert mode in this file, so I'm just going to add the IP address. So I'm just going to type in hello world info. So what this does is this sends requests from helloworld.info to Minikube. Okay. So I'm just going to click escape, save this file. So once that is done, what we're going to do is we are going to verify that the ingress controller is directing traffic. And we are going to do this using the curl command. You can see successfully the command has been executed. So if we shift to the browser, you can see that it's up and running. Okay. Once that is done, I'm going to shift back to my terminal. So now what we're going to do is we are simply going to test our ingress. Okay. So in the next part of the session, we'll be testing our ingress. So testing is the absolute same way. You're simply going to be accessing using the curl command, and it will just give you the output of what you are accessing. You can create many deployments, and you can also add these deployments to your example ingress.yml file. And this will also be tested and it can also be applied.
Let's talk about what is Helm. You can think of these 3 points when trying to understand Helm. First, it is a package manager. Second, it deploys charts. And third, it reduces complexities. But what does that mean? Let's talk about these points one by one. First, Helm is like a package manager but for Kubernetes. If you're familiar with installing via terminal in Linux, you can think of Helm as yum or snap, which helps you install packages. Helm does the same thing but with Kubernetes. Second, it deploys charts. So, the charts or Helm charts are nothing more than a packaging format used by Helm. The chart is a file collection describing a set of Kubernetes resources. These Helm charts help you define, install, or upgrade your Kubernetes apps with ease. And lastly, Helm is meant to reduce complexities and chances of duplications. As the chart structure helps developer deploy apps faster without much coding, Helm provides structured way to manage Kubernetes applications with ease. Now, let's look at what is a Helm chart. To understand this, you must understand that Helm chart is a package. These packages contain YAML files that contain configuration and other necessary details for the application. These package file or chart are then used by Helm and then deployed on Kubernetes. This install or uninstall process is simplified using Helm. Thus, it makes deployments and management of applications easier. So, why is Helm used and when to use it? First, let's look at this key point. Even to make a simple deployment in Kubernetes, you need a minimum of 3 YML files. Creating these files from scratch can be boring and time consuming. After you do this, you can make your deployment, and this is the same even if it is a very simple deployment. This is what Helm solves and why it is used to manage applications in Kubernetes. Once you install Helm and have it configured, you can install production-ready applications from software vendors such as MongoDB or MySQL with just one simple Helm install command. On top of it, if you ever need to remove installed applications, it is as easy as installing. Coming to the point about why Helm is used, it offers significant advantages. First, it simplifies deployments, and the process becomes seamless. It is easy using Helm charts to set override defaults in the values.yml file, allowing software vendors or admins of chart to define the base setting which is optimal for proper functioning. Second, it reduces complexity or duplication. Once the chart is built, it can be used over and over again. The fact that one can use the same chart for any environment reduces complexity of creating something for development, testing, and then for production. It boosts productivity. Software engineers are good at writing software, and the best use of their time is in writing software. Helm make it possible to deploy softwares with single click and saves time and boosts productivity. And it smooths the Kubernetes learning curve. It is not a big surprise that learning for Kubernetes and containers is long. With Helm, this is simplified and allows developers to not require understanding every single aspect of Kubernetes objects. Now, let's talk about when to use Helm. Although from a high level, both Helm and Kubernetes operators do the same thing, you can think of using Helm for simpler deployments. The reason being is that as your team size grows and the project scales up, you might need direct control over your custom applications. Thus, many people agree to not using Helm for custom configurations. When working in an enterprise level, using Helm might make things more complex and hard to navigate through. But to make things clear, Helm can be used even with complex applications. It is just that sometimes it is preferred and sometimes it is not preferred. Now, let's look at the chart structure. You can create a chart in your terminal by writing Helm create followed by the name of your chart. After creating the chart, you will end up with a list of files in the directory of the chart name you provide. Here, we will be talking about three main things, which are the chart.yml file, the templates directory, and the values.yml file. So, let's look at these. The chart.yml file is a metadata file. This file contains information about the chart, including version and other such details. The values.yml is the default configuration file. This can be thought of as the heart of Helm, containing necessary configuration details for the chart that you create, and the template folder. This folder usually has a service.yml and deployment.yml. This folder contains the templates which are combined with values files and creates a valid Kubernetes manifest file. We will see all of this in the demo shortly. So let's dive right into the demo. And here we will install Helm first and then create our chart. After doing that, we will make a simple deployment using Helm install. So here I have my master and worker node set up, and all I'll do is SSH into my session. So here I have Kubernetes installed and configured. I can verify that using kubectl. As you can see, we are in the ready status and my worker node is connected and the master is the control plane. So here, the first step that we need to do is install Helm. You can find out the details by typing into your browser Helm install, and that will take you to the main page. As you can see, on this page, you can find how you can install Helm in your operating system. Since I'm using Ubuntu, I can use either these commands, which are from here, or I can use the snap. Now, I'll be using this command because it's just one single command, and paste it into my master node. Now that Helm is installed, I can go ahead and create a chart. I do this by typing Helm create followed by the name of my chart, which I'll say demo. And as you can see, we have created. So as you can see here, this directory was created right about now. So now I'll just type in tree demo to see the directory. So it looks like I don't have the tree installed. So let's fix this. So now that I have tree installed, I'll go ahead and then type tree demo. So as you can see, this looks very familiar with the chart structure that we talked about before. Here we have the chart.yml file, we have the templates directory containing the deployment, service and other YML files, and then we have the values.yml file. So the objective of this demo is to create a very simple deployment, and what we are going to do is launch an Nginx service. So here, what I'll do first is that I will edit the values.yml file. And to do that, what I'll type is vi demo and then values.yml. So this is a basic configuration. Here, what I'll do, as you can see here, I have my Nginx and all I need to do is configure it so that I can deploy it on my Kubernetes. So I'll make some basic configuration changes and later on I'll deploy it. To do that, I'll make some changes right here. And then I'll provide some override values. Next, I'll make it the type node port because I want this to be accessible. And now I'll go ahead and save all these changes. Now that it is done, all I need to do to launch this is type in helm install demo followed by the name of my chart, which I provided, and then I'll provide it with my directory, including the values.yml file. And with that, we get a confirmation saying it has been deployed. So what I need to do is type in these three commands to get the port number. So here I get the port number, that is 30563, and if I am able to curl this, it means that we should be successful. So as you can see, we get a response from our Nginx that we just deployed. We can again verify this by going to my browser and typing in my external IP address followed by the port name. And as you can see, our Nginx server was successfully deployed. In this way, you can launch applications using Helm in your Kubernetes clusters. This was just a simple demonstration, but even complex apps can be deployed using the same process. So feel free to experiment and do the same process, or maybe make some changes and try to figure out how things work in Kubernetes.